So we covered, in the first half of the lecture, we covered heteroscedasticity. What does heteroscedasticity mean? What are the implications or the consequences of having non-constant variance for the errors? And then how to detect and test for that, and then how to correct for it. We did the same with autocorrelation. So what do we mean by autocorrelation? And how to test for autocorrelation? What are the consequences of having autocorrelated or serially correlated errors? And then how to test for that, and then how to deal with it. So now we're moving on to the last point I would like to cover in this lecture, which is the model specification. So one of the assumptions is that the model is correctly specified. So when we talk about model specification, we mean so many things. But before we jump into what that means, you should know that there is no such thing as a perfect model. So it's very difficult, really. So, but we do our best. We try to avoid all these issues with the specification. So mainly, we should make sure that we include all the important variables in the model. So if you want to explain the behavior of y, of a variable called y, then you need to include all the important variables, the important x's that explain it. Don't just include variables for the sake of including the variables, so they have to be relevant. And that's the second point. You need to think of your functional form. Is it linear? Is it log-lin? Is it lin-log? Is it log-log? Etc. So you need to think about there should be no measurement errors when measuring your variables, y and x's. And you should account for outliers, the probability distribution of your errors, and non-stochastic regressors. You have fixed regressors and repeated samples, and no simultaneously bias. So what I'm going to cover, I can't cover all these points. I'm going to cover a few, 3 points. We're going to talk about what would happen if you drop important variables, what would happen if you add variables that are not relevant to the regression, or what would happen if you have measurement errors. So 3 of these problems. So the first one is called omitted variable bias, which means when there is an important variable that you do not include for one reason or another, you do not include in your regression. How this is going to affect your estimation. So in that case, let's say this is my correct model, where y should be explained by x2 and x. That should be x3. This is a typo in the notes. Okay. So x2 and x3. And for one reason or another, I estimated this model where I dropped this x3 by mistake, or I don't know about it, or I can't measure it, or whatever reason. For that reason, my estimated B2 will be biased, and this is by how much? So basically, you're looking here, it will depend on beta 3 and the correlation between x2, or how much x2 and x3 are correlated. So that means your estimation will be biased. Okay? Do you remember? Do you want the estimation to be biased? What do you want about the estimation? Unbiased. So what do we mean by unbiased? Unbiased means that this one, the expected B2, should equal beta 2. Okay? But because you dropped an important variable, then the estimation of B2 became biased, and this is by how much? Okay? So in the case of omitting or dropping important variables, you are falling with this problem, the omitted variable bias problem. So let's look at an example. In this example, I'm using data about education income. So in this data, we're trying to model, let's say, family income. And in this data, we said The correct model is family income should depend on the husband income and the wife income. So HE here, the husband income and wife income. And this is the number of kids who are less than 6. Okay? So let's say this is our correct model. This is the model that we should include. So these are the estimated coefficient, but for one reason or another, we actually dropped these two variables and we estimated the model just using the first variable. Okay? So look at the estimated coefficient and compare this with this one. It's different, and it's actually it's much bigger, it's much higher, yeah? And that's because of the bias. Okay? That's because you dropped these variables which are important, and that affected this. So that show you with heteroscedasticity, with autocorrelation, we had the same coefficient when we corrected for it. We still have the same number, the same coefficient, because it doesn't affect. It is actually still unbiased. The OLS estimated for heteroscedasticity or for heteroscedastic error and autocorrelated error, they're still unbiased. So that's why you have the same coefficient. But with omitted variable problem, you actually have biased estimator, and that's why you will have a different estimator here this time. So this is the wrong model. This is the model that suffer from omitted variable bias because we dropped these two variables which are relevant, they are important. That's why we have a different value for the estimator. Okay, so how about if it is the other way around? If we include variables that they are not important, okay? So the first case, you dropped variables that are important to the regression. You should include them. We have this, the estimators are biased because of that, as a result of that. So if we add variables not economically meaningful or relevant, they're not really related, and some people just add more variables and they see, oh, R squared is increasing every time I'm adding new variables, so that's good, that regression sounds good. That's actually a mistake. Okay? So I'm here showing an example that is very, like a typical example for this situation. Like, this is data like it's made of, these extras, so this is the correct model, and then you add these two variables. I call them extra x5, extra x6, and these are just made up. So these are not really related at all to these to the family income, the phenomena or the variable that we want to explain. And that is the problem. So you sometimes when you add these sort of variables, it affects the model in case of, if they are not important. Okay, so they are likely to be insignificant anyway. So you see, this is 0.6 with high p value. This is high p value. That means these two variables are not really relevant to. So how should I test for whether I have omitted variables or not? There's a set test where you can estimate a model and obtain the y hat, which is the when you estimate the model first, you call it the restricted one, and then you estimate it again, including y hat as an additional regressor, and this will call this the unrestricted one because it has additional term y hat, and you could put more like y hat squared, whatever, and that then you compare between the restricted that without the y hat and the unrestricted with the y hat, and your null hypothesis is that the restricted model is correct. So if you reject, that means the model you have doesn't have the correct form. So that means, or it's not correct. That what means. So in that case, let me show you an example. So in this case, what we did here, I estimated the same model. So remember, this is the restricted model, and then what the function for that is reset test, and then you pass to this function the name of your regression model that you saved it in mode 3, I just call it model 3 here, and we look at the p-value. So what does that mean, this p-value? It's very small p-value. Well, it's less than 5%. What should we conclude if the p-value is less than 5%? You reject the null hypothesis. So the null hypothesis means that this model is not correct. Well, the null hypothesis is correct. The model is correct. Okay? So rejecting it, that means it's not correct. And this is one of the drawbacks. So what? What should we do then? That's one of the main drawbacks of this test, that there's no alternative specification or no guidance on how many and the number of power terminals to the right hat to include in this model. But anyway, so the idea is just one way to look at it, but the conclusion here is you should be careful about the omitted variable bias or including variables that are not relevant to your model. And usually, how do I know that? Usually, do you remember what we said in the first lecture? What did we say about regression? It doesn't establish causality. You need to get this from theory, exactly. So that theory should tell me what variables are relevant, what variables are not. Why should I think that x2 or x3, whatever they are, affect y? Okay? If you put any data in R, you will get results. Okay? It's the same way when we talked about the example about the rainfall and the crops. Like the causality here is just was based on the very basic intuition or common sense. Anyway, so just moving to conclude, before we conclude this lecture, the errors or the measurement errors. So we talked about omitted variable bias. We talked about including irrelevant variables that are not important to the regression. And now we're just going to finish off with what if we have issues with the measuring the variables that enter the regression. So if the issue with the dependent variable, so it's not that serious. Okay, of course you should make all effort. You should make sure you're not having any measurement error, but it's still it causes some issue, but it's not as serious as the case with the regressors. Because in that case, all the estimators are still unbiased, but the estimated variances are larger than in the absence of such errors. But when you move to the, so that's why I'm saying it's more serious when the errors are in the x's, because it created biased estimators. Okay, so when you have a measurement error in your x, or measuring the regressors or in your independent variables, so that means your all these estimators are biased. Okay, and that is why it is more, it's a more serious issue and problem. So in that case, you could use an instrumental variable if you have any doubt about one of the variables that you think it suffers from measurement error. You can use a proxy, and this is something we'll talk about later in this module. Probably in week 8. Okay, so let me just sum up before I ask you the question. So what we said today, we talked about heteroscedasticity, autocorrelation, and then we moved to model specification. We didn't cover everything about model specification. We looked at 3 things. We talked about 3 points. The first point, omitting important variables, adding irrelevant variables that are not important, and then if there's measurement errors.